I'm talking about what the test is going to look like, and then we'll jump in and we'll go through all of the lectures you guys have gone through so far, and I'll point out the things that are important for you guys to know, and I can answer any questions that you have. So this exam, this exam is going to be just like the last one in terms of format, so you're going to have some multiple choice questions, you're going to have some fill in the blanks. You'll have 3 short answer, and then 4 essays, and you'll choose 2. And so, again, on your exam, make sure that you are highlighting the ones that you want me to grade if you're writing on more than 2, unless it's like totally obvious which 2. Okay, so does anybody have any questions about format? What about content? Is there anything before I start going through slides that you just particularly know that you have questions about and you want to go through? All right, well, we'll start from the beginning. Okay, so chapter 8, 10, 11, 12, and 13, I think. We can see for sure when we go through, so we're just going to start at chapter 8, which is where you guys started this unit with Dr. Etheridge. And so initially here, you guys talked about sort of an overview of synaptic transmission, which this should all be stuff that's pretty common to you guys by this point, so I don't anticipate anybody needing to memorize this slide, for instance. Where you're really going to start looking over material for this exam is with the differences between electrical and chemical synapses. And so this is primarily stuff that you talked about here in this lecture, and then the rest of the unit, you guys talked about chemical transmission, right? And so the characteristics of chemical transmission that are listed in this PowerPoint in particular are going to be things that you should generally be familiar with because that's what we spent the rest of the unit talking about. And so the electrical is, for this particular PowerPoint, probably where you want to focus. So there's not a ton of information that's important for you guys to memorize for electrical. So here, this is a good image to review if you want some sort of a pictorial description of the differences that you have here. So you can see this is your chemical synapse. You have a neurotransmitter that's being released across the synaptic gap from the presynaptic cell to the postsynaptic cell, right? And so where with electrical synapses, you're obviously going to be using gap junctions. And so this slide is sort of a good overview of what an electric synapse is, what an electric synapse looks like. And while you don't necessarily need to memorize each individual line, it is important to understand what an electrical synapse is. As long as you seem to have a good understanding of that, you should be good for this. So here's another image for you if you are interested in that. So the uses for electrical synapses is important. And so, again, while you don't need to memorize every single piece on this slide, it is important to know that electrical synapses are essentially going to be used for things where you need quick, sort of explosive activation of synapses, right? So examples are things like heart beats, right? You want that to happen regularly and quickly for that system to work appropriately. And so this slide, again, is another one that if you are thinking logically about what an electrical synapse does, if you're presented with a question about an electrical synapse, you should be able to logic out, oh, these things fit with fast reflexive action, or these things don't. But it's up to you if logic is not your thing. This slide is good, and it will give you a general overview of what electrical synapses are responsible for. Any questions on that? So, again, this is a pretty good overview of some of the different mechanisms that you're going to see electrical synapses used with. So not only are they important for transmitting messages, but you can actually have nutrient transmission, like you will in Schwann cells. You can also have electrical transmission through the astrocyte networks, again, to transmit different things in terms of ions or neurotransmitters, etc. Does this make sense? All right, so chemical synapses, this should be, again, something that's familiar to you guys. So you don't need to memorize this slide if you feel pretty comfortable with the rest of the material that you've talked about in this entire unit, right? We've spent the last however many weeks since exam 1 essentially talking about chemical synapses. Again, this should all be pretty general information that you guys should feel pretty comfortable with. So neurotransmitters are going to be your primary messaging molecules for chemical synapses, and the idea is that though they're not necessarily as fast as a gap junction or an electrical synapse, what you do get with a chemical versus a electrical synapse is that amplification of the signal, right? So with gap junctions, you're getting one signal, it stays pretty much the same, but with chemical synapses, you can get actually a greater signal in the postsynaptic cell than you had coming from the presynaptic cell, right? Does this make sense? So this is a pretty good theme across this whole chapter. There are many things that you can sort of compare and contrast, and those are really easy things to ask questions about, right? So what is the difference between a chemical and electrical synapse? So those are things that as you're studying and as you're going through things, if you can compare and contrast things, know the differences, right? That's a good place to start in your studying. So this is a good slide, right? So different types of chemical synapses. You guys spent a lot of time talking about the differences between ionotropic and metabotropic. And so that is something that you need to know. So you should be able to understand and list the properties of an ionotropic receptor, and you should have a firm understanding of how that is different from metabotropic. So remember your ionotropic, I'm going to move so you guys can look at the picture. Ionotropic, remember that's going to have your pore, right? So you're going to have neurotransmitter binding and ions coming directly into the cell, right, to do whatever they're being sent there to do. Whereas with a metabotropic receptor, this is your second messenger system, right? You guys had we did a whole chapter on second messengers. So again, the idea of a metabotropic receptor should be really familiar. And so here you have a neurotransmitter binding on a receptor on the pore, and then that creates some sort of secondary action that's going to activate messengers within the cell for some sort of other purpose. Yeah?
If we get an essay question asking us to like describe a metabotropic reaction, are we gonna need to know like the G proteins and like how those come off?
Yes. So generally understand how this works, but remember you guys spent a lot of time talking about cyclic AMP. So there are other when we go through the second messenger chapter, there are other second messenger systems like there's a slide I think for the endocannabinoid system. You don't need to know that, but know cyclic AMP pathway and how that works as a second messenger with a G protein coupled receptor. So if you understand though that example really well, you are generally going to understand how metabotropic receptors work. So when you're studying, I would focus on that particular pathway. It's sort of a two birds with one stone thing, right? You are at the same time understanding really well a pathway that you guys spent a lot of time on in class and would make a really good question. And you also, if you're understanding that really well, you're going to understand the general principles of metabotropic receptors. It's a good question. So, in this case, for this picture, you see that the effector protein, right? So this has been activated by your G protein right here, and that's then allowing ions to cross across the membrane, right? But remember, particularly like for the cyclic AMP pathway, this effector protein can do other things within the cell as well, right? So it doesn't necessarily have to involve the letting in of ions either way. Make sense? All right. And that is the end of that one. So any questions about chapter 8? All right, so this chapter spent a lot of time talking about the differences between excitatory and inhibitory inputs, excitatory and inhibitory receptors. So again, these are really easy things to compare and contrast, right? Excitatory versus inhibitory. And so what you see here, and this is something that should be generally familiar also from our human neuron lab, is that your excitatory and inhibitory postsynaptic potentials, so what we see happening over here, those are going to be taken up by the dendrites, right? So different axons are sending different excitatory or inhibitory input, and then these different inputs, so our postsynaptic potentials, are all going to sum right? And then you're going to get some sort of action by the trigger zone at the action potential, or at the axon hillock, I'm sorry. We'll go through that a little bit more as we go through the rest of these slides. You do not need to know gray type synapses. This is sort of extra added information. That's not something that you're going to be asked about on the exam. It is important, of course, to understand what an excitatory postsynaptic potential is, though. And so again, these are happening at the dendrites, right? These are being taken in by the dendrites and used by the axon hillock to make a decision about whether or not it's going to send an action potential. And remember, these in and of themselves are not action potentials, right? They're very either small hyperpolarizations or depolarizations that are going to influence whether or not an action potential is going to be fired. So if you need an excitatory response, if you need an action potential to be fired, you need lots of EPSPs, right? So there are a number of different ways that you can get your EPSPs, which is where, as we go through, the temporal and spatial summation comes in. And so we'll talk about that more as we go through the rest of these slides. So we've talked about our input, right? So now it's time to talk about the receptors and the synapses. And so you guys talked a lot about glutamate and about GABA as being potentially inhibitory or excitatory. And so we know that glutamate here, particularly central nervous system glutamate, is going to be your primary excitatory neurotransmitter in the CNS, whereas GABA is going to be your primary inhibitory neurotransmitter in the CNS. And then you have glycine for your peripheral nervous system. And so it is important to know that channels that are gated with glutamate, you need to know why these are excitatory. And so they are excitatory because they're equally permeable to both sodium and potassium. So essentially what this means is that you have those ions are going to flow equally well across the membrane, which is going to cause the reversal potential. So where you're getting equal amounts basically of sodium and potassium coming in, you're getting no net flow of ions, right? This is going to be your equilibrium. It's going to be close to zero, right? And so when you think about where your threshold is, down there around -40, if your potential when glutamate-gated channels are open is going to be close to zero, you're going to get an action potential, right? And so that's what makes these glutamate-gated channels excitatory. So main points when you're looking at this, it's equally permeable to sodium and potassium, and this equal permeability essentially causes reversal potential to be more positive than resting membrane potential, right? More positive than the threshold, which is going to cause a depolarization, and it's going to cause an action potential. I hear lots of like typing and writing still, so I'm going to give you guys a few minutes or a few seconds. Okay. All right, so you have two different kinds of glutamate receptors. So you can have your ionotropic. So remember, if you're thinking about the meaning, if you're asked a question about an ionotropic glutamate receptor, you should be able to figure out what's happening just by knowing that it's ionotropic, right? And so it's going to directly gate sodium and potassium. It's always going to be excitatory, right? So essentially what's going to happen is glutamate's going to bind, sodium and potassium are going to flow across the membrane, and you're going to get that excitatory input, right? And so examples of ionotropic glutamate receptors are AMPA and MDA, and I always say it wrong, kainate. So with this list in mind, you guys talked very, very heavily about NMDA, right? NMDA and how that impacts long-term potentiation. So from this list, it's going to be important for you guys to understand how an NMDA receptor works. And so we'll go through that in just a second. But again, if you're asked something, if you were to be asked something about a metabotropic glutamate receptor, remember this is going to be indirect gating, and that's about as specific as your knowledge needs to be for metabotropic glutamate receptors. Right? So think, again, while you're studying, in addition to what we're talking about now, when you're going back through your things, the things that you guys spend a lot of time on, those are probably going to be the things that the exam's going to focus on, right? So properties of your NMDA receptor, you do need to know these. So it's going to be permeable, and we'll go through all of this. So you have permeable to calcium as well as sodium, potassium. You also need extracellular glycine to bind, to open the channel. And then the main sort of crux of these channels, which is what we're going to focus on most when we go through them, is they're what you might call a coincidence detector, because they're looking not only for glutamate to bind, but also for a certain membrane potential, right? So these are both voltage and ligand-gated channels. So this is, if you can understand this image, if you can explain what's going on here, you're going to be good to go. So we'll take it, we'll go through it, we'll take it all the top. So over there on the far side, you have a glutamate binding site, right? And so these are, of course, and it's a glutamate receptor. The binding of glutamate is going to be necessary to open this channel. But what you also see is the channel is blocked on the inside by a magnesium. And so even if you have glutamate bound, if that magnesium is still within the channel, you're not going to get any flow of ions. And so what has to happen is you have to have something that forces the magnesium out of the inside of the channel. And that's where the membrane potential comes in. So you want a depolarization, you want your membrane potential to become more positive, which is then going to force this magnesium out of the channel and allow ions to flow in and out. And so this works with long-term potentiation. You can think of it as a coincidence detector, because it's essentially detecting like the coincidence of when glutamate is bound and when the membrane is also depolarized. And so essentially what this looks like when you're also sort of taking into account the presynaptic cell is we know that glutamate's bound, and so the presynaptic cell has obviously released glutamate, right? But what you also want to happen is that presynaptic cell is still excited enough that it's depolarized and this membrane is depolarized. So the depolarization, the excitation of those two membranes at the same time is what's going to give you your depolarization here, cause that magnesium to move, and then coincidence, you have both of those things happening at the same time. So you need glutamate for if you are writing, if you have to write about this on an exam, you need glutamate to be bound, and you need a membrane depolarization to move magnesium out of the center of the channel, right? So those are sort of your two main things that have to happen for this receptor to work, right? And this is coincidence detection because it's essentially detecting when the presynaptic cell and the postsynaptic cell are excited at the same time. Lots of voice cracks.
What was the second thing you said? Depolarization.
So the presynaptic and the postsynaptic cell, it's detecting when they're excited at the same time, right? Does that make sense?
But I mean, what do you need for to knock out magnesium?
You need the depolarization. Yep. Because that's essentially, it's making the membrane more positive, right? And so because magnesium is also positive, it's going to want to move away.
Of both sides or just one side?
It's going to come out this way.
I mean, depolarization of that side?
It's going to depolarize the whole membrane. Yep. Make sense? Any questions? All right.
I have a quick question.
Yeah.
How does that relate to the neurons all firing in sync?
So if you're getting excitation at the same time, it's going to be happening very quickly. And so that's what makes it sort of fire in sync.
Okay.
And that's what makes, essentially you're making those connections stronger by having them all fire together, right?
Okay.
Does that make sense?
Mhm.
Okay. And so that then, this idea that they're firing together, you're having neurons come in, or you're having ions come in. This then interacts with things like memory, long-term potentiation. We're going to skip over here. By trafficking the more AMPA receptors up to the postsynaptic density, right? So what this looks like. So this is a good overview slide for long-term potentiation for the stuff that we just talked about. In terms of memory, in terms of long-term effects, so we've talked about how the channel is actually going to open. So what happens is when calcium comes in, right? So these receptors are also going to allow calcium to come in. Calcium sort of kicks off that whole system that allows the AMPA receptors to be trafficked up to the surface, right? And so those AMPA receptors are your sort of more typical glutamate receptors, right? And so essentially what happens with an AMPA receptor is you're having calcium and sodium, or you're having potassium and sodium, which makes them an excitatory channel, right? And so by putting more AMPA receptors on the postsynaptic density, you're essentially allowing for greater excitability of that cell. And so because there's more receptors, when glutamate enters the synaptic cleft, you're going to have greater excitation because there's more receptors, right? There's more places for glutamate to bind. And so essentially what this allows for is faster excitation and stronger excitation. So this is that idea that you see something once, right? And then if you continue seeing it, so you're continually getting those excitatory activations, you might say, it's going to continue making that channel more excitatory, right? And so that's one of the things that we see with memory is actually going to strengthen associations when you're learning. Does this make sense? Everybody following along? Okay, great. All right, so this is a fun little way to remember. So neurons that fire together wire together. So if you have your neurons firing in sync, you're making those connections stronger. So that speaks pretty well to your question. All right. So I don't like that image quite as much. This one is great for giving you sort of the whole process after we've let calcium in, right? So our NMDA receptor is up here. So remember, we have, looking at sort of a more global view, we've had glutamate bind, right? So it's glutamate right there. Glutamate is bound. There's also been a depolarization of the membrane that's allowed magnesium to move out and allowed sodium and potassium, and also, importantly, in this example, calcium to come in, right? So calcium works with calcium calmodin 2. It then interacts with this RAS system here. And what you see is that the RAS system comes down and essentially allows this little guy here. So this is our AMPA receptor. It's attached to myosin, which is our motor protein. And it is then trafficked to the surface, and then stargazin, our fun little star guy right here, then takes them back up to the postsynaptic density where they're going to be most useful. So generally understanding how these different terms, how these different molecules are involved is important, but you're not going to have to list from start to finish this cycle. So be able to recognize the names, know where they're involved, but I'm not expecting you to list start to finish how this works, but you should know how an NMDA acts in terms of being involved with long-term potentiation. Make sense? All right. This one is one of the tougher concepts, so if you decide later that you have questions, send me a message on Canvas, or I'm going to schedule an extra set of office hours. Feel free to come in then and we can talk about it more. All right, so with long-term potentiation, the opposite of that, or you can call it the opposite of that, would be long-term depression, right? And so this is essentially we've now at this point, we'll assume that we've trafficked a large number of our AMPA receptors up to the postsynaptic density, and now we need to remove them, right? And so this can be kind of tricky for some students because it does involve, you're still having glutamate binding, right? It's still an excitatory input. But what you have here is, instead of lots of firing and lots of activation of an NMDA receptor, what you get is occasional firing. So that's those instances. Let's say I get up here and put it in a over oversimplified example, right? Let's say I get up here and I teach you guys a dance routine, but I teach it to you wrong, right? So you've learned it, right? You've had activation of those pathways, but it's not correct, right? So the next day I come in and I teach it to you correctly, right? So this pathway is no longer going to be firing. And so when I teach you the new routine, you might think, oh, okay, I don't need to know that anymore, right? So you're going to have the activation of the pathway enough to essentially say, yeah, I don't really need this anymore. And because it's an occasional firing, because you're not getting the same systematic continual firing that you were getting with long-term potentiation, the occasional firing is enough for the cell to essentially say, okay, we might not need all of these receptors up here anymore. It's time to take them back down and lessen the sensitivity. So what happens then? You get occasional, you haven't had activation of that pathway in a long time, you get activation, one quick brief, let's say, and then what happens from here is that these AMPA receptors are taken, essentially the calcineurin takes in the calcium ions, it then comes up and activates your dynamin here, which pulls the cell membrane in. So this would be an example of endocytosis, right? And then these receptors that are on the outside of the membrane are going to be detached and then recycled, right? Does this all make sense?
Do we need to be able to describe that?
No, generally, the idea of long-term potentiation, but you do not have to describe this. Second. Yes.
And just to clarify, you said that ultimately the receptors are removed,
Yeah.
like gradually?
Yep, yeah.
So
So where this gets, yes, good to remember. So you're removing, so in a way, it's not necessarily inhibitory, but it's lessening the likelihood that you're going to get super, super high excitation with glutamate, right? Because you're going to have less receptors. But the important thing to remember is that this does still take an excitatory input. So glutamate is your excitatory neurotransmitter. So that's sometimes hard for students to wrap their heads around because you're getting excitation of the synapse, but ultimately what you're doing is lessening your sensitivity. Okay, but as long as you guys feel good about that, we're good to go there. So know generally what an NMDA receptor does. I wouldn't spend a whole lot of time on this slide. No, yep, you're good. This is the functions of NMDAR. So we just spent a lot of time talking about long-term potentiation, so that's going to be something that's important for an NMDA receptor. That's what we focused on in class, so that's what, for the exam, I would expect you to understand, is that the interplay between NMDAR and long-term potentiation specifically. So this is less important. We will talk as we go through about glutamate toxicity, particularly in certain disorders, but not as important for you guys to know here. All right, so when you think in inhibitory synapse, think of hyperpolarizing, right? So your excitatory, they're going to be depolarizing, your inhibitory are going to be hyperpolarizing. And for this example, it is important to remember that GABA is going to be your inhibitory synapse. In the end, this is going to make your cells less likely to fire. This is all stuff that I think is probably you guys are probably going to feel pretty comfortable with. All right, so again, we talked a lot about glutamate and about GABA. So these are the receptors that I would expect you guys to know for the exam. So know that GABA receptors are going to be inhibitory because they're allowing calcium, or they're allowing chloride to come in. So chloride is going to drive that membrane potential down well below threshold. It's going to keep it very negative, which is going to make it harder to fire an action potential, right? That's what makes GABA an inhibitory receptor. Again, you have your different examples. Ionotropic are going to engage chloride. Metabotropic are going to open potassium channels, but the idea is the same. What you're getting is a potential that's lower than resting. So no action potential if you're where you're sitting, your equilibrium is below or is more negative. need summation to get an action potential or not, and the ratio of EPSPs to IPSPs is going to be what is determining essentially whether or not you're going to have excitation of that cell down the axon. So there are two different types of summation. You have your temporal and you have your spatial. And so temporal is going to be multiple postsynaptic potentials at the same location, right? And so